Well, welcome to Chapter 5, Question 1, all about terminal settling velocity. Now, the most well-known equation for terminal settling velocity is, of course, Stokes' drag equation. I'm not going to derive Stokes' drag equation because there's plenty of other videos on YouTube that do just that. So please consult them if you're interested in the derivation. All I'll say is that we have down here the viscous drag term due to Stokes, which is, ignoring the minus sign which isn't here, it's 3 times pi times the viscosity of the fluid times by the particle diameter times by the velocity. That's the drag expression, and that would be in terms of newtons, and it's just equating the drag force with the buoyed weight force. So that's the weight of the particle, taking into account the natural buoyancy from the surrounding fluid. Okay, so that's Stokes' law. We will be using it in a short while, but I'm not going to go through the derivation of it. What I want to look at here is what happens when Stokes' law is no longer applicable, when we have sufficient turbulence in the system. And what do we mean by turbulence? Well, if we just have a quick look at this, it's an animation, but I've not started it just yet. But this is a green ball that is settling downwards, and you can see that the fluid is, relatively speaking, moving upwards, which explains why we have these arrows just here. These are, in fact, streamlines going past the green ball. So as the green ball sinks down into the fluid, if it was just viscous drag, there would be no turbulence in the region that I've just highlighted here. So it's the turbulence here, or the inertia of the fluid that is part of that turbulence, that makes the drag force that much greater than you would get from simply the viscous drag term, which is of course Stokes' law. So there's an additional drag. The drag we're talking about here is form drag, because it depends on the shape of the particle. A feather has a very different form drag to a spherical particle that's shown just here. And the form drag gets to a point where it can actually totally dominate the total drag. So drag is obviously therefore equal to the form drag plus the viscous drag. Say we can get to the stage where the viscous drag becomes negligible compared to the form drag at high velocities. So when this green ball is settling downwards at high velocities, we have substantial turbulence in the wake of the particle. So if I can just kick the animation, if it still works, into action, yep, it's this turbulence, this circulation of the fluid on the following edge to the particle, not the leading edge, the following edge to the particle. And that's what's causing the drag over and above the viscous drag. We've still got the viscous drag occurring even at high velocities or high Reynolds numbers, but it's the fact that we've got this additional drag that causes slowing down of the particle compared to what we would expect Stokes' law, a Stokes law based prediction to show, because Stokes law only takes into account the viscous drag. So that's the position we're in. Now let's have a look at some let's have a look at the problems themselves. And before that disappears underneath me, I just want to point out that what we have here are specific gravities of 2.8 and 1.0 for the particle and the fluid respectively. And specific gravity is relative density, so clearly what we're talking about here is a density difference between the solid and the fluid that is going to be equal to 1,800 kilograms per meter cubed. 1,800 kilograms per meter cubed. The fluid is of course water. Water has a density of 1,000 centimeters cubed. So I can push that underneath me. The most important result is illustrated there. Okay, so the approach we're going to take here is one of the Haywood tables. Why? Because the Haywood tables is valid for all conditions. All the other correlations, the Archimedes, the Galileo, and all the other ways of solving this problem at high velocities, where form drag is relevant, it depends on what the Reynolds number range is. Haywood tables works for all of them. So we have these rather bizarre parameters called P and Q that need to be calculated. And the question tells you that pH is that value, and you'll notice the SI units are meters to the -1, and if you multiply pH times by x, of course that gives you a dimensionless number, which is good. We like taking the logs of dimensionless numbers. Logs of dimension numbers can be problematic, so it's good that we have the right units here, and indeed by the same sort of logic, Q down here, UT over Q, is going to have, of course, the same units as velocity. So in fact, the answer to that question, getting ahead of myself, is velocity, because again we need that dimensionless number. Okay, so what we're doing here is comparing these two rows. The takeaway message of just here is that we've got these two rows here that are settling velocities, both in meters per second. However, this one is solely due to Stokes, so we're going to apply the simple Stokes settling equation to work out these settling velocities, and quite frankly they should be right for relatively low sizes and therefore relatively low settling velocities. But Stokes' settling equation is not going to be valid when we have significant form drag. So we're really expecting these two to be poor values, whereas just here we kind of would expect to have a very similar value, whether we apply a technique that only uses viscous drag, which is Stokes, or whether we apply a technique that is valid for all Reynolds numbers and includes all the form drag as well as the viscous drag. So we kind of expect these two to be similar, shall we say. Okay, well, we need to do some calculations. Let's just do it on the 50 micron size rather than repeating it for 100 and 1000 as well. So what we need to do first of all is to calculate log P times X. Well, we're told the value of P just here. X is 50 microns. So if I kick up the spreadsheet to act as a calculator, we have in the spreadsheet a value of, let's just go for it, 2.87 times 10 to the 4. That's our value of P. The value of X is 50 microns. That's 5 times 10 to the -5 meters, because we're going to be in SI units. And the log to the base 10 of that is 0.15. Let's call that 7, 0.157. So P times X is 0.157. So we're looking at something in the order of 157 just here. Now, the big question is, how do we actually calculate the value of U, which is the terminal settling velocity, over Q, which is this Haywood parameter again, all to the power, log to the power 10. How do we get that? Well, we get that from the tables. So keeping in mind log px is 0.157, let's move on to the tables. So if we come down, I'll come back to this in a moment. Let's move on to the tables first. 0.157. Okay, these tables are in the appendix of Fundamentals of Particle Technology. So they're printed out in the tables. They're also available on the website particles.org.uk. and the value of log px that we're after is 0.157. So it's a bit like a vernier scale. If we come down to here, that's our 0.1. Okay, 0.15 takes us into this region just here, 0.157. So we know that the value we want is somewhere between these two, biased towards the 0.06 rather than the 0.05. So we're somewhere around about here in terms of our answer of what the log u over q value should be. So I'm going to say that's minus 1.072, which is roughly speaking where it should be just there, minus 1.072. Okay, so if we go all the way back up to our value up here, that was, I'm going to start over here, minus 1.072. Now if we put that, now you've got to bear in mind that is the value of this term here, this term of log to the base 10 terminal settling velocity, which is what ut is, over qh, okay, is that value. So if we anti-log it and then multiply by q, that should give us ut. Okay, we need to work out what q is first. It's shown in this equation just here, and in fact it is answer A. Okay, so it's 2.87 times 10 to the minus 2. So let's kick our spreadsheet back up again. I have kept a placeholder for the value because I've called that just 1, but actually we need to introduce the value we've just looked up, which is minus 1.072, and if you put that in, that gives us a value of 0.084 for terminal velocity divided by q. If we use the value of q that we know is 2.87 times 10 to the minus 2, then I know it's a long-winded process, but eventually we get there, that the terminal settling velocity is 2.43 times 10 to the minus 3. Okay, so that gives us a value of the terminal velocity of, in just here, of 2.43 times 10 to the minus 3. Okay, so that's the terminal velocity coming from the Haywood's approach. How does that compare with Stokes? Well, the interactive questions on the website provide you with a nice little table of results. They are questions because it is actually a question as to what the value of A is just there. But we're interested in this row here, or this column here, sorry, the 50 micron column. So we've just worked out that the settling velocity is 0.0243. Let's just have a quick check of that with yep, it was 243 times 10 to the minus 3. So we're in business, we've got the right value there, that's good. So we've just calculated that using Haywood tables. Now what do we get with Stokes' settling? This actually says a slightly different value. That's interesting, but it's very close, within rounding errors, let's say. Here is our Stokes' equation. If we're dealing with a, I'm going to actually answer this question first before getting on to the Stokes' settling for a 50 micron particle. You'll see why in a minute. There is logic behind my argument. So what we have, first of all, is the particle diameter squared. If it's 10, sorry, if it's 1 micron, that's 10 to the minus 6. If we're squaring it, that's going to become 10 to the minus 12. Then we've got the density difference, which we know was 1,800 between the densities of the fluids, the particle and the fluid. And then, of course, we know we've got 9.81, which is the acceleration due to gravity, and we divide that by 18 times by the viscosity, which is 10 to the minus 3. So let's put 0.01 in there. And if you work that out, that comes out to be 9.81 times 10 to the minus 7. And I see I've just run that underneath me. Sorry about that. I'll move it. Down a little bit maybe. Yeah. Okay, that's quite logical. We're going to get that because that clearly 18 and 1,800 there gives us a few tens. Clearly we've got 10 to the minus 3 down here, so that helps to cancel out some of the 10 to the minus 12s. And of course the only thing we've got left with number wise is 9.81. So the answer is 9.81, and if you work out all the powers there, it comes out as 9.81 times 10 to the minus 7. I'll just push that back up again. Okay, so the Stokes settling, predicted Stokes settling velocity for a 1 micron particle is 9.81 times 10 to the minus 7. A quick look at the Stokes settling equation, and you'll notice that it's proportional, the settling velocity is proportional to the diameter squared. Everything else here is a constant. All these other terms are a constant for a given particle density, fluid, and viscosity of the fluid. Okay, so if they're all constant, then if we go from 1 to 10 microns, then we would expect the settling velocity not to be a factor of 10 higher because it's diameter squared, but a factor of 100 because we're squaring the difference. So that would be, so the answer A is in fact 9.81 times 10 to the minus 5. And of course when we go from 10 microns to 100 microns, we're going to have the same argument. It's going to be 9.81 times 10 to the minus 3, and indeed it is. And then on to another order of magnitude, 2 orders of magnitude, as we jump again. Okay, so why did I do that? Well, because we now know that we've got a 10 micron particle is 9.81 times 10 to the minus 5. And if we're going from 10 to 50, that's 5 times difference. So therefore, the settling velocity according to Stokes is going to be 5 squared times. So I would expect that to be 25 times the 10 micron settling velocity. Okay, and that gives us this 0.00245. Right, let's come back to the slight difference between the two. Is it just a rounding error? No, it's a bit more significant than that, because don't forget this is settling velocity by Haywood, and it takes into account the form drag. This is settling velocity by Stokes, which doesn't. It only takes into account the viscous drag. So in other words, we would expect the settling velocity by Haywood to be slightly less than the settling velocity by Stokes because of the additional drag that this equation, this technique, takes into account. So it's a wholly logical way around. What we're saying here is that the error in the Stokes settling equation is small. It's 2 in 243 if you compare these two values. So 2 in 243 is such a small percentage. Stokes' equation is okay. It's valid at 450 microns. The error is so small. However, when we look at a 100 micron particle using the same technique via Haywood to come up with a settling velocity of 0.0088 against 0.0098, then the error is now becoming significant. It's 10 in 88, which is something in the order of 12-13% error, which is probably not good enough for an engineering calculation. And of course, when we come to a millimetre sized particle or 1,000 microns, the error is enormous. The form drag is absolutely enormous, and the error now is just huge when using Stokes. So Stokes is a really good equation because it's simple, but it's only valid up to a limited particle size, or more correctly, a limited Reynolds number, particle Reynolds number. Okay, so that's our complete table that's filled out. I've sort of jumped around a little bit here into the Stokes's, into the Haywood tables and into the Stokes and the Haywood calculated settling velocities. So, but the takeaway message is that Stokes is a fantastically simple equation. Use it by all means, but do check the particle Reynolds number. And the particle Reynolds number is quite simple. We'll use a prime to differentiate particle Reynolds number from flow Reynolds number. Every chemical engineer remembers Reynolds number to be du rho over mu. Well, the characteristic linear dimension here is of course going to be the particle diameter rather than the pipe diameter. Rho is of course still there, du rho over mu. So we also need a velocity, and over mu, the coefficient of dynamic viscosity. So that is the velocity that we've just calculated, and rho over mu, these terms just here, are the density and the viscosity of the fluid, because that's where the turbulences take place. If you have a highly dense particle, it'll give you a very high settling velocity. So that is effectively where you're taking into account the density of the particle. If it's very dense, it gives you a high settling velocity. Don't use the density in Reynolds number of the particle. Use the density of the fluid. They're all both terms here are fluid-related properties, not particle-related properties. So why should the Stokes' velocities of the larger particles always be greater than those found in practice and given by the Haywood's table? It's because of the form drag, which the Stokes equation doesn't take into account. Stokes' drag only takes into account one type of drag, and that is viscous drag, whereas in reality, at the high Reynolds numbers, we'll have form drag as well as the viscous drag. We don't lose the viscous drag, it's still there, it just becomes much less important. Okay, well, I've mentioned the particle Reynolds number. Check the particle Reynolds number. We are hoping for a particle Reynolds number to be less than 0.2. So long as the particle Reynolds number is less than 0.2, arguably that's the wrong way around, then that is our threshold for minimal turbulences, where form drag isn't so relevant to us. So long as the particle Reynolds number is less than 0.2, we can use the Stokes' settling velocity. When the particle Reynolds number becomes greater and greater, above 0.2, the proportion of form drag gets greater and greater, and we lose the ability to use Stokes. Okay, thank you.